So, as mentioned, I work at Sumo Logic, and I'll get into that in a little bit. But what we're going to talk about today are graph mining and logs, machine log data. And what I hope that you get out of this talk is just enough kind of knowledge and information and some examples to sort of get yourself started thinking about these kind of problem domains and these techniques, and just enough knowledge to sort of be dangerous and get off the ground with trying to apply these graph mining techniques to maybe some of your own event data sets. And so this talk's going to involve explaining some of the machine log context in Sumo Logic a little bit, what we do. It's going to have some graph mining basic concepts to just kind of get started, and really step through some application examples and try to develop sort of a framework for thinking how we can develop graph mining approaches for our various problems. And what's also really important to go over here is what we are not going to be talking about, which is very specific talk about tooling or scaling. And so, there are a lot of different products, services, and libraries that facilitate graph mining work and often sort of do some of the heavy lifting or help you do the heavy lifting for scaling and that kind of thing. And we're not really going to dig into that in this talk. It'll be more sort of thinking about how you can even begin to conceptualize your problems and your data sets as being suitable for a graph mining approach. So very, very quick, we'll go through this. Just graphs. What are they, right? You have nodes. You have edges. They might be undirected, and they're connecting the different nodes. They could also potentially be directed, and they can be used to separate the nodes into components by whether or not they're connected by the edges. And this is an undirected example. There's sort of an analogous concept for directed graphs. There's a notion of paths and reachability, where we say, how can you get from one node to another? Can you even get from one node to another? What is the shortest path to get from one node to another? So this is, again, I'm kind of just going to move really quickly through the sort of the very basic stuff, and then we'll get to some fun examples. And the next thing would be subgraphs. So you don't always have to process the entire graph at once. And maybe you're going to just look at some subset of the nodes over here. And a property of nodes is degree. So maybe we're going to say, how many neighbors does a given node have? And so you can see that one node is more popular than all the others in this graph. It has 3 neighbors. There are 3 edges connecting it to 3 other different nodes. And finally, there's sort of a notion we'll get into about the metadata. You can have metadata associated with your nodes conceptually. In this case, it's a very simple sort of just color labeling scheme. And so nodes can have different properties. Edges can have properties. These are all sort of kind of side channel metadata that can be in your graph representation. And people for many years have been very interested in graphs for their applications. So there's kind of the obvious social graph that many people have talked and studied and researched a lot, where the nodes are individuals and the edges indicate a social or professional relationship. And so you can see here my PhD advisor is friends with the cat with fruit on its head or something, right? There you can think of the web pages, and their links could be directed edges. And a local search engine startup very famously kind of exploits this information to try to rank web pages based on how popularity kind of flows through this graph over pages. But because of my line of work and my personal interests, what we're going to be focused on mostly are sort of these notions of system graphs, where individual nodes are going to be services or machines or potentially virtual machines or software components, and edges indicate various dependencies, interactions, API calls, ways that these connect with each other. So in this really simple kind of schematic mock-up, you have maybe whenever you call the API of one of your favorite services, it hands off the request to some internal authentication service. This internal authentication service then says, oh, is this user really authenticated? And then it calls a different service to say, is this user's company really a valid customer of ours, or something like this. So these kind of distributed services architectures are they're kind of ubiquitous in modern distributed systems for a variety of reasons that are kind of outside the scope of this talk, having to do with modularity and operationability and things like that. So this is what I'm really interested in. And how we often interact from a data perspective with these is via log messages. So pieces of software constantly writing out log data. And these logs contain a whole bunch of information. So they kind of answer the basic questions. When did a particular event happen? For example, you logged in and we're trying to authenticate. When did this happen? And where? Which node in my architecture did your login request hit? Which software module handled the request? Who are you pretending to be or saying you are, or who are you? What is the actual execution context, and who is really handling this code? What actually happened? And this can often be an English language or natural language sentence. User X tried to log in to host Y at time Z with credentials, that are associated with an account type Z, whatever, something like this. So that could be key value, it can be natural language, but it sort of says what actually happened. And this log data, just for full context, is the stuff that we're very concerned with at my employer, Sumo Logic. And so this will be just a little bit, give you some context for the sort of problems I'm interested in. Sumo Logic is a cloud-based log management and analytics solution. So the idea is you take all of your huge piles of log data, throw them up in our cloud system. You can set up dashboards, you can run queries, you can set up alerts, you can do analyses, you can detect anomalies, all sorts of fun stuff. I highly encourage you to play with it. But I am going to mention right here that in this talk, it's going to be very conceptual graph mining for log data. And it is not a feature-by-feature rundown of stuff that the Sumo Logic service does. So I'm not just going to show you a whole bunch of features that Sumo Logic has, but more talk about conceptual graph mining things you can do with this kind of data. Some things you can do with Sumo Logic that I'll be talking about. I encourage you, like I said, to play with it. We have a free trial, all that good stuff. But this is the basic context for why I'm concerned with these problems and how I think about them. And so in that context, you have interactions and connections that are present in this log data. So there's going to be a lot of graph nature underlying the situations and the realities that are captured in the log data. For example, in the previous example, a human machine. You are interacting with some remote service or some app or some website or something like this. And all of these interactions almost certainly are being logged. And they're therefore suitable for sort of behavior analysis in terms of this graph of actions. How are you patrolling the site? How are you clicking on things or not clicking on things? And this is potentially very interesting to the proprietors of apps, websites, and this sort of thing for a variety of reasons, two of which are sort of just basic behavioral analysis. They'd like to know that if everybody hits their landing page and then it takes too long to load and they go away and they're unhappy with it, that's something that from a business perspective, people like to know. And if you're doing lots of strange, non-standard, or abusive things with their app or website, from a security perspective, they'd like to know. Another kind of graph you can build is machine-machine. And this would potentially be this services architecture, these API calls that are happening. And again, any interaction with any modern kind of distributed system is going to kick off a wide variety of sort of internal calls behind the scenes in that system. And how those machines interact with each other is something that you are very concerned with if it is your job to make sure that the whole system is functioning smoothly. Because in the giant distributed system, something going bad somewhere could potentially have sort of ripple effects or cause bad customer experience or things like this. And just for completeness, of course, there are human-human interactions in the real world. We're not really going to talk about those. So the classic example of something going wrong and you being upset about it is you're interacting with some website or service and you get this error message. There's a failure, something timed out, something like that. And under the hood, you're hitting this one front-end server that's kind of serving up the app or serving up the UI. But under the hood, it's probably calling something else. And there's another log message associated with that. Potentially, as before, maybe that service is even calling another service or calling a different service, which calls yet another service. And so here we have this rather branching and non-trivial chain of events triggered off by your attempt to interact with a website, app, or service. And this graph of the calls between the components is really interesting to the people, again, responsible for operating and maintaining this website, because in this case, something way down the chain has failed, it didn't propagate quite so nicely to the user, and then that is actually what caused the problem. So when you file the support ticket or the complaint or whatever, you're going to say, I had a problem at this time trying to do this thing, and the person responsible for investigating this is going to have to kind of put together the pieces and recover the original situation of what happened kind of down the stack that caused this problem. And you can actually think about this in a graph term, right? So we've been explicitly saying the nodes are these different events, the different system components. And you can say, let's try to build a connected components problem out of this graph data. And here for each log line, we can parse out basically these request UIDs, these session IDs. And so we have a bunch of fields for every log line. And not every field is present in every log line, but we have these values. So then we can try to build a graph where the individual events or components in your system are the nodes. And we're going to say that they have an edge between them if they match on any of these fields. And so before in the previous example, we'd say, okay, this session ID on each side of the remote calls, kind of build up this chain all the way through. And once you have this graph, then you can run connected components on it. And now you sort of have this partition, this collection of log messages, which are actually associated with that user trying to log into the service before. And so what was perhaps a huge sea of millions and millions and millions of log messages, by building up a graph of connection between the log messages and following the graph from the user interaction of interest, you can actually recover this connection all the way through to the actual event that happens somewhere in your infrastructure. So this is kind of just a classic troubleshooting thing. And it's actually so classic that maybe you don't even have to connect the components yourself. There's a variety of sort of libraries and third-party frameworks and tools for instrumenting your code to basically make the graph nature of these remote calls a first-class concern in sort of your logging, monitoring, instrumentation infrastructure. And so Dapper from Google is kind of a very famous one. There's a nice research paper about it and all that. And there's kind of a variety of other open source and sort of closed source tools that follow on to this. And in this example here, again, we have this blue calls green, and then green calls red and yellow. And a lot of these tools will actually even give you this kind of nice chart where you can see how long different components of that call chain took, right? And so this is great. If you have this, then the data is already sort of in a graph-like format, and we can do other fun stuff with it. So another use case would be online shopping. So again, here we have users interacting with your site, and you have pieces of your site interacting with external infrastructure, maybe payment suppliers or a third-party service that validates that your mailing address is real. All sorts of stuff happens under the hood when you click buy on anything. And in this really simple example, we're going to say that the different states and actions of some e-commerce website are the particular nodes of the graph. And you're kind of traversing them whenever the user is interacting with that site. And again, the things you might be interested in knowing are my users, is this user behaving really oddly? Or is my site behaving really oddly? So in this, because it's so close to the actual point of sale in an e-commerce context, it's very important to get these things right. This is where the money actually changes hands. So how are we going to do this? We're going to try to identify visits, again, kind of by the connected components, or if we have our own nice instrumentation. So in this case, what we've taken here is this graph of different actions and interactions of your website or your app or whatever. And we've created this graphical underlying idea, and each visit is a connected component in that graph. So next, we're going to do this featurize thing. I'm going to say this a bunch of times, where we're going to take some properties of the graph, the connected components, how many times they visit each node, how many transitions there are between edges, various things like this. And we're going to turn this in to these actual sort of numerical features that are more treatable by machine learning or statistical approaches. So let's say that we've done the following, and here are a bunch of visits and a bunch of times, some properties of the graph. How many times did a given visit hit a given state? And now they're all sort of fixed length vectors. And the thing about fixed length vectors is that they are a long history and a wide variety of techniques for dealing with them from a modeling, statistics, and machine learning perspective. So in this kind of little toy drawing to the right, this is just two-dimensional projection of a bunch of data points. And it's fairly obvious that one of them is rather different than the others. And what this is kind of implying here is that, okay, this session, for some reason, has visited the cart state 1,347 times. Okay, well, if I'm the operations person or the security person associated with this e-commerce site, I'll probably be a little concerned about that. Either something is weird with my site and it's spuriously redirecting them to that node over and over and over, or this is not an actual person but some kind of bot trying to mess with my site or scrape my catalog or something like this. So this is basically fixed length feature vector outlier detection, which can be done with a kind of wide variety of statistical methods based on this graph data that we've transformed into this nice feature length, fixed length feature vector representation. So an alternate way to turn this graph of user interactions into a fixed length feature vector is to consider the edges. So before we basically said, let's look at the nodes. How many times do we hit each node? Now we're going to say, how many times do we traverse each edge? And again, maybe there's some edge transition, which is very, very unlikely or unusual, or maybe even it should be impossible. And if you see that a huge number of times, you're going to have a fixed length feature vector that any kind of simple statistical modeling, it's going to really pop, and it should be detectable as an outlier or an anomaly in that sense. And this is a very general technique that can really pay dividends in this wide variety of situation. And so just for some more context, there's the notion of a fixed length feature vector, and this is a really simple toy data set that's sort of it's very kind of famous in the history of statistics, and it's this Fisher iris data set where you have a bunch of measurements of different parts of a flower along with the actual species of iris it is. And the thing is that lots of sort of papers, there's whole UCI repository full of data sets just like this. This is what people have been very focused on handling well from a statistical modeling and machine learning standpoint for very many years. And so there's a really wide, very deep body of techniques and approaches that can be applied to data which is massaged into this format. So one approach, which I'm basically focusing on in this talk, and it's not the only approach, but it's definitely, it gives you sort of an 80-20 way to really quickly and really effectively do some really cool stuff with graph mining, is to basically focus on the following question. How can I transform my graph being some representation of the actual phenomena of interest, these calls, these user actions, anything that sort of has this graphical nature? How can I transform it into this fixed length feature vector representation such that we can sort of treat it with these classic sort of statistical machine learning and modeling approaches? And so this is this featurizing idea. So how can we transform different kinds of graphs and different entities within graphs into features? And again, I'm going to be focusing kind of on machine log data examples because that's sort of my interest. But maybe we're interested in nodes. And again, these nodes could have properties. How many times did we hit a particular state? What is the other metadata associated with the user doing that kind of visit? The connectivity of the node is another property. So earlier we talked very briefly about degree. How many neighbors does a given node have? And if a node, we can model the statistical distribution of degree and sort of say, is that machine connected to way too many other machines? That's something that's really unusual. What are the neighbors of that node like? So another thing you can say, what are the properties of the nodes which are immediately connected to that node? And so all of these are potentially choices that you could use to encode a fixed length feature representation of your data which was originally graphical. And again, so the application here maybe it would be, I'm going to model the distribution of the degree of nodes in my network where it's remote connections. How many remote connections are there in my log data from the outside world to a given machine, or from one of my machines to all of my other machines? I can build a connectivity graph of these remote connections on my network, and then take the degree of the node and say that's my fixed numerical feature, and then sort of do something on that, right? You could fit a parametric distribution or something. Now, again, edges. Maybe edges are really interesting, and so these edges can also have properties. In the previous examples, especially in kind of an ops context, maybe you're really interested in the latency or the time that transpires between two logged events in your infrastructure. So if somebody makes a remote call from one service to another, and then it's a very long time before you see the log for the other side of that call, you can say that edge is associated with that latency property, and that's something that you could be potentially modeling with just, again, maybe a simple parametric model or something. Which nodes is that edge connecting? Is that really an unusual connection? Do I never see somebody connect from machine A to machine B usually, but now I do? That's something else that maybe I'm really interested if all of a sudden two machines which never talk are talking a lot, right? As if I'm a sort of security conscious person, that might be something I would like to hear about. Then again, whole graphs. So in all the previous examples where it was kind of a user session on the e-commerce site or something like this, you can treat the connected component as an actual graph itself, and you have access, you can featurize the properties of the nodes, the properties of the edges, or even the kind of higher level connectivity properties of the graph itself. What are the subgraphs it has, all of this kind of thing. There's a lot even richer representation that somehow, how do we turn a graph into a fixed length feature vector? And then these are potentially ways to do that. So yeah, unusual remote access. So maybe it's SSH, it's something like this. The question that people are very often interested in is, are these observations typical? And again, we could say, did this machine connect to each other? Count those edges. What is the depth of the subgraph, or the length, the diameter of this graph? So maybe people usually connect remotely to one machine, and they hop to at least one, maybe at most one other machine. If all of a sudden you're seeing these really long remote connection chains where they go from machine to machine to machine to machine to machine to machine, that might not be normal. And that's something you can quantitatively capture in this remote access graph by saying, what is the maximum path length of one of these remote connections? What's the maximum diameter of one of these subgraphs? Or again, user edge. Maybe this user does not ever log into that machine, and this is something that's really unusual. Again, this is something that's pretty straightforward to quantify. You can count it, and then you can treat it statistically with any number of 1,000 kind of machine learning or statistical modeling approaches. So another kind of thing you maybe want to do, this is a little more exploratory, is maybe you want to understand your internal architecture, so your internal API calls. So again, you're either logging or instrumenting or something, but you probably have this distributed architecture, and it's different services are being exposed to each other, and it's very complicated, and who's calling whom, and you want to chart that out somehow. And so you want to understand how different services are maybe being called. So let's say that I have some really expensive or complex or valuable internal service, and I want to just do an exploratory scan to understand within our system who calls this service and what do those calls look like. And I want to know, how are these calls the same? Is there a common thread? Or how are they different? How do the callers of my internal service vary? And one kind of little fancier graph mining tool you can turn to is frequent substructure mining or frequent subgraph mining. And this is something that there's an enormous amount of research on because it's computationally a little more formidable. But the idea is basically that you have some collection of graphs. So again, these graphs are sessions, they're calls, they're transactions. It's something you've created, this connected components or whatever, and it's some notion of a graph. You have a collection of many of these graphs. And you want to find the subgraphs, which are the motifs. So if any of you were here this morning for the Excellent Time Series talk, there's this talk about motifs as features, essentially. And subgraphs are very much like the analog in the graph world to the time series motifs that were discussed this morning. So you want to find maybe subgraphs that occur in more than T graphs. And this would, in a very kind of simple toy example, you have these three graphs, these are three call chains, and some computer would hopefully be able to look at this and say, well, this is the common motif. This one is appearing in all of them. So this is really interesting. So in this example, what you're able to do is potentially sort of treat that as the fixed length feature now, is whether or not each of these subgraphs is present in various calls. And so maybe there's one that is present in all of your calls. All of the calls to this internal subsystem have this little subgraph pattern of nodes calling each other, and it's because it's authentication and everybody has to do it. Okay, that's kind of interesting. Maybe some of these calls to the internal infrastructure are behind a special caching layer, and so then they have this little different motif that sort of says, oh, these are cached calls, and so they have a little extra sequence of calls out to some other cache before they hit the thing. Or another one would be a shadow version of the service. So maybe you're running two versions of your internal service for testing or performance or debugging or something, and the ones which hit the shadow cluster have this other unique signature of a particular subgraph being present in the data. And so this is just another way where we've taken something that's really a little involved. We've broken up the underlying data into the graphs. We've got the connected components to get it to a level of observations. And then we've done the frequent subgraph mining to basically featurize it one step further and say each of these graphs is now represented by a feature vector, which is 1 or 0, depending on whether or not all of these individual subgraphs are present. And so this, again, there's a wide variety of approaches you can take, but this is sort of the feature-based graph mining. And so trying to zoom out just a little bit to say, okay, what is the general approach for graph mining in this style of approach? And step one would be to determine your goal. What are you really interested in? I want to know about remote activity that seems really unusual. I want to know about understanding different customer flow through my website. It could be, I want to know unusual access patterns. And this is very heavy on domain knowledge. So this is going to be, you really have to know your domain, your logs, your data, your problem set. The next step is to turn that into a graph. If it has some actual graph structure, encode the log data, the relationships, the entities into a node edge graph formulation. It's kind of a mix of domain knowledge and some graph mining knowledge. Then once you have that, frame your initial question graphically. So in the idea of what's remote access, unusual remote access patterns, maybe I'm really interested in a node that has a wildly unusual high out degree because that's a compromised node and now they're SSHing from that box into all over our infrastructure. And so this, again, is kind of a graph mining heavy part. Next, featurize that. So somehow take that graph characteristic, that property of a graphical element that you were interested in, and somehow represent it as a nice numerical vector thing that is suitable for treatment by machine learning and statistical methods by a wide pool of sort of experts in that kind of thing. And so this is kind of a mix of, again, knowing your graph, knowing what's reasonable, and knowing a little bit about the machine learning model you want to throw it into. And then finally, you can apply some modeling technique, right? You just fit parametric distribution to it, do an SVM classifier, do logistic regression, any number of these kind of statistical or mathematical models. Now you have your initial problem, your initial question about graphical data, and now you have it in a nice, really crisp kind of machine learning treatable thing where you can really do some cool analysis. So that's the zoomed out general approach that I hope is useful to people and kind of do some cool stuff with your own log data or your own graph data. Build your graph data out of other data. Do stuff like this to it. I think there's a lot of application for this kind of technique, and it's really fun to play with, to boot. So to wrap it up, acknowledge to the extent that we do support this kind of stuff in the Sumo Logic product, it was the work of a big team, including Jack Cheng, Martin Castellanos, Liu Gao, Yu Chen Zhao, and Ariel Smoliar. So that was the team that worked on this, and I have to pitch Sumo Logic. We're selling a product. There's a free trial. Dump your log data in the cloud. Go nuts. Build graphs. Fun times. Of course, we're always hiring. I'm always hiring. I'm recruiting. Come talk to me. We're doing interesting, fun stuff. Graphs. Good times. All right. Thanks.